Why, hello. We're going to be building a rate law based on a mechanism. What is a mechanism? Well, it's just a step-by-step account of the elementary steps, basically the mini reactions that take place in an overall reaction. In this particular case, we're synthesizing nitrous oxide. Cool. Let's get to it. Now then, when determining a rate law for a reaction using a mechanism, the most important step to hone in on is the slow step, or the rate determining step. A reaction can only proceed as fast as its slowest step, which is why that slow step is going to dictate the overall rate law of the reaction. So we can write a rate law based off of the slow step, and that's exactly what we're going to do. So I'm just going to write out here, rate is equal to some constant k, classic, and then we've got N2O2, and then times N2. Okay, and that is technically accurate, but is it a good rate law? No, it is not. Why is that? It contains an intermediate. An intermediate is a chemical species that's produced in some step and then used up later in a subsequent step. As we can see, the N2O2 was produced in the first step and then used up in the second step. We can't have intermediates in a rate law because they're coming, they're going, their concentration is too transient. We can only write rate laws in terms of reactants or catalysts. So now we're halfway there. We've got our foundation. Now what we want to do is we want to use a little bit of chemistry and a little bit of substitution to help make this rate law in terms of only reactants or catalysts. In this case, we only have reactants. So how do we do that? Okay. Well, while the slow step is taking its time and slowly going, what does this first step have a chance to achieve? A chemical state called equilibrium, where the forward rate and the reverse rate are equal. So what I'm going to do is I'm just going to replace this arrow here with an equilibrium sign. And now what we're going to do is we're going to exploit the fact that while this slow step is going and everything's bottlenecking up here, this is going to have a chance to reach that equilibrium. So now we're going to write a rate law for the forward reaction and the reverse reaction. We're going to set them equal to each other, and then we'll do a little bit of substitution and call it a day. So in order to write a rate law, I'm just going to say that the forward rate has an arbitrary rate constant of k sub f, and the reverse reaction has some sort of k sub r. Okay, cool. Now then, let's write a rate law for the forward reaction and the reverse. So for the forward reaction, it's going to be k sub f times, and then we've got NO reacting with NO, so it just be NO squared. And then we're going to set that equal to a reverse rate law, which would be k sub r times, and then N2O2. Great. Now that we have this written out, our goal is to solve for the concentration of the intermediate in terms of the reactants. So in order to do that mathematically, what do we have to do? Well, divide both sides by k sub r. So we'll divide this side by k sub r and this side by k sub r. Constant divided by itself, well, that's just going to be 1. And a constant divided by a constant, that's just a whole new constant. We don't care what it is. So I'm just going to call this k arb for arbitrary. Doesn't matter. We're not solving for it here. Now that we've solved for the intermediate in terms of reactants, what we can do is substitute in our working rate law, and then we'll have a good rate law. And you can finish things off. So I'm going to take this, I'm going to plug it in, I'm going to substitute it in place of N2O2, and then what we're going to get is our new and improved rate law, which is rate is equal to a constant times a constant, just another constant. I'm going to call it KOBS for observed. Sometimes you'll see that. And then let's see, we've got NO squared times, and the N2 didn't go anywhere, And that is a good rate law. Okay. Thank you very much for your time. Have a great day.